All right. So there's two kinds of current. One is alternating current, and the other is direct current. So alternating current, this is like the current will go from move in this direction and then it moves in the opposite direction and it rotates back and forth. So this is how homes and buildings are wired. So like most things are alternating current. And this helps like the same electrons can move throughout your house always. And direct current is the current going in one direction. So that's like what we did yesterday on the PhET simulation. Like you could see the little electrons all moving in a circle, and they always are moving in the same direction around the circle. Maybe it's like clockwise or counterclockwise, whatever. But you're always going to have that same direction. Whereas with alternating current, they alternate directions. That's why it's called alternating current. So real quick, which one is alternating current and which one is direct current?
The left is direct and the right is alternating.
Yeah, that's exactly right. So this one, the current is always positive. It never changes. It never fluctuates value. Whereas with this one, with the alternating current, if you're having current that changes directions, you're going to have to pass through a current of 0. So it's just kind of like motion. Like if you're running to the right and then you need to change to move to the left, you can't just all of a sudden change directions. You have to slow to a stop and then turn around. So it's the same idea as with like slowing to a stop and changing directions. Okay, so we're gonna skip, we were gonna do like a investigation of which one is the most sensitive between a galvanometer, ammeter, and light bulb. But instead, I'm just gonna tell you the galvanometer is the most sensitive. So a galvanometer is this thing. So if you see here, and this will come and become important for your explanations, it's in microamps. That's what that like fancy U means, is micro. And that's like super, super, super small. Times 10 to the negative 6, super small. So this is a super sensitive instrument, and basically that little needle, and you can kind of see it if I move this around, the needle will point to wherever the current is. So if your current is changing directions, that means it's alternating between positive and negative. So if on a galvanometer you have alternating current, that needle is going to go back and forth, back and forth, back and forth, back and forth. If you have constant current, it's going to move to one location and just stay there. If you have no current, it's going to stay at this 0 point. So on Thursday, we're going to show you a galvanometer, and you're going to have to tell us what that's saying about what's happening in the circuit. An ammeter, this is probably a more like if you ever take another physics class, you will probably use an ammeter because they're less, even though they're less sensitive, they generally speaking serve their purpose. Like they're good enough for most circuits. So an ammeter, this is an example of an ammeter. And so this ammeter is, you like change the dial to the amps or microamps. and then you plug in your wires and it reads the current. So just FYI, if you ever take another physics class or electronics class or engineering with circuits or something like that, you're probably going to use an ammeter, not a galvanometer, because we don't need it to be that sensitive usually. But if you're trying to prove if there's current or not in a circuit with like as close to 100% certainty as we can, you're going to want to use a galvanometer. Okay. So on last Thursday, which feels like forever ago, you were watching the magnetic field notes. So I'm just gonna like kind of give you a rundown on this slash a review of this. So a magnetic field is just this force distributed in space. So for example, this magnet, this bar magnet, has a magnetic field that's distributed in space. So that's like why if I bring a magnet close here that it can attract still, it's because there's a force on it all the way out here, because that force is distributed in space. So that's why you can influence other objects. We also talked about this in terms of like domains. That's part of the reason why ferromagnetic objects, so those are things like metals that aren't magnets themselves, but they can attract to magnets. Those things, that's why their domains will all align together. It's because of the magnetic field. So a compass is how we're going to determine if there is a magnetic field present. So with a compass is actually a magnet, and so if you bring it close to the magnetic field, it's going to align with the magnetic field. It basically points in the direction of the magnetic field. So this language of aligning itself to the magnetic fields is super important. So you're going to have to say that. That's like a big physics concept, is that a compass aligns with magnetic fields, or it points in the direction of magnetic fields, because that piece of information is going to tell you if there's a magnetic field and what that magnetic field is doing. So something that's kind of interesting is that if a magnetic field is changing, so like if you bring a bar magnet close or far away, and we'll see an example of what that looks like, then that compass is going to move so that it's aligning with that changing magnetic field. Okay, so this is station number 4, which I think is page 9 in your packet. So this is what magnetic fields look like. So you can kind of copy down, like, if I were you in my packet, they kind of look something like this. So they're kind of this like circular pattern a little bit, with these like tendrils kind of on the outsides. So what these are is iron filings, and iron is a ferromagnetic substance. So when you put a bunch of iron, basically like iron shavings, close to and with like in the influence of a magnetic field, then those iron filings are going to move so that they align with that magnetic field. So that's what's happening here. Okay. Then this is what compasses look like if you bring them under the influence of a magnetic field. So because compasses align with magnetic fields, notice this is like a very similar sort of shape. And I'll show you in a second what I think you should copy down in your packet. But notice like the north points away from the North Pole. So the north part of the magnet, the red part, points away from the North Pole of the magnet. It always is pointing away. And if you look at the south end, those compasses are pointing towards the South Pole, right? So that north point is pointing towards, they point towards that south, and they point away from that north. So this is what I think it's helpful to look like in your packet. Because sometimes drawing those compass arrows is a little bit confusing. So you don't have to put in like every single one, as long as you have a general idea of, oh, near the South Pole, they're all going to point towards that south. Near the North Pole, they're all pointing away. And then around the centers, they're pointing like kind of parallel slash towards the south or away from the north. Okay. Now, this is what a changing magnetic field looks like. So this is station number 6. So there's a couple different ways that you can create a changing magnetic field, but basically it's just by moving the magnet. So this video shows a couple different changing magnetic fields. So you'll see like we have these 4 compasses. If I start to rotate this magnet, those compasses are also moving back and forth. So it's similar to the galvanometer. Even if you just move it side to side, those compasses are going to move back and forth. So what I would say is important about this station is that when you bring a compass close to a changing magnetic field, those compass needles are going to alternate back and forth, back and forth, back and forth. Okay. So that's pretty much all we have today. The one thing though, I don't know if you all know, but there's a virtual spirit week happening. And um I have circuit stuff and I have Lego